Anshumali Shrivastava from Rice University, where he's an associate professor. Professor Shrivastava did his bachelor's at IIT Kharagpur, where he received a silver medal, and completed his PhD at Cornell. He's won numerous awards over the course of his research career, including the LSF Career Award, the AFOSR. He won a NIPS Best Paper Award in 2014, an Outstanding Paper Award at MLSys just this last year in 2022, and a Most Reproducible Paper Award at SIGMOD in 2018, among others. So today he will be talking about probabilistic hash functions and hash tables, a new paradigm for efficient AI training and inference. Over to you.
Thank you for having me, and thanks for taking the time. Always a pleasure to talk with the brightest mind of India around here. So I'm going to talk about, a marriage between statistics and data structures. And hopefully I'll be able to convince you that there is enough meat for exploration there. So I'll start with the motivation, and again, I belong to the machine learning community, but I'm primarily an algorithmist, right? So I'll talk about what the real problems that we are seeing in machine learning, and why I would imagine people from especially theoretical computer science are the probably only community of folks that can address some of these critical issues. So I'm just going over we all are hearing all the news that AI is making, GPT-3, right? I mean, all the large language models, what Google can do and all. What has happened over the past year, if you see what is going on is, people are experimenting a lot. So there's one thing is like Google, Microsoft, they have capabilities to create a hypothesis and validate it pretty quickly. And that is the reason why we are seeing this fast progress. But what has happened over a period of time is that the model size is increasing a lot. So I'm just trying to cite a paper that Google published in 2017, in which they were trying to, train a large language model on a corpus that has about 1 billion tokens or billion words. Sorry, 100 billion words. And they trained about 100 billion parameter model for that. And in the abstract, that says that, well, we need that model size to absorb all the variations in the data. And in the same paper, they say, well, this is not what our ambition is. We have a data which has 1 trillion token. So it has trillion words, and we'll train 1 trillion parameter model on it, which I think they fulfilled in 2021. Now, what is going on here? So I want you to think from an information theory perspective. So let's say I'm trying to solve some of the hardest problem. Let's say question answering, right? Google question answering. You type a question, it gives you an answer. And at the end of the day, it's a program, and a program is a function. So in a function, you're inputting a question, and you're expecting the function to provide you an answer. If the question has enough variation, and if the answer has enough variation, the memory footprint of the function cannot be small, period. That's information theory, right? And where does the memory footprint of the function comes from? In machine learning jargon, it's the number of parameters in the neural net. And this paper gives you the feel of what is going on. If I have 1 trillion word corpus, I probably need trillion parameters to at least memorize some sort of variations for each word, what each word means, and so on and so forth. And this is happening across the year. It's even known as neural scaling law in the machine learning community, that you give bigger models and more data, and you get more accuracy. And in fact, that's the only consistent way of how we could move the performance or the accuracy bar high. Right? I mean, there are architectures, people will come up with all the novel ideas, but it will be shot down by some other novel idea. But at the end of the day, the trend is clear. These are like some of the popular models, and I'm plotting on the number of parameters, and obviously this is time. Now, there is a lot of thing going on in neural networks. Maybe we need this kind of a network, that kind of a network. People have now trying to come to a conclusion that maybe what type of network is less important. It's just the size. Right, so you can actually replace attention. I don't know how many of you know these, these jargons in machine learning world, but there is attention, convolutions, blah, blah, blah. These are like specific kind of architectures, and there has been debate about, we need this for vision, we need this for NLP, and now all that debate are like fading. Damn, that guy again showed the same thing that I was talking about with something completely different. But what has remained is that the size, right? So anything reasonable and big is all you need kind of a scenario. And in fact, it's also, as I mentioned, smart engineers are driving the AI revolution rather than any smart architecture, right? I mean, if you're following the literature. So we are in a point of time where essentially it's a trial and error process, right? So there are companies which hypothesize an idea about I'm going to solve a language model problem or like maybe let's say an image generation problem using neural network. They come up with the hypotheses, and the faster they can validate the hypotheses, the faster they are going to make progress. But what does validating a hypothesis means? So if you're a small company or a reasonable company with limited amount of budget, it's basically what is known as PhD descent. If you know gradient descent, there is a term called PhD descent. You hire a whole bunch of PhD students and you tell them to come up with interesting architectures based on their experience. You validate them, then they refine it, you validate them until you get to the desired outcome.
Sorry, but you just say in the previous slide that smart architectures is no.
So is smart architectures not there, but you still need a lot of hacks. You still need a lot of hacks to train these things. But you know, like, and if you see, smart architectures are useful if you cannot go to that size. That is what I'm saying. So if you're a mid-tier, like for Google, they can do an automatic neural architecture search. For mid-tier companies, they have to do PhD descent because they have to come up with smarter ideas, right? But that's also the clue that there is still some thing needed there. Now, people will talk about that, well, AI model training is one thing. What about inference? Inference I want to achieve because if, let's say, Google search is deploying a neural network, every time somebody types a query, it hits a deep learning engine. And if the deep learning is very big, then that costs a lot of energy. So efficient inference is important, but well, efficient inference is again a model search. It's searching for a cheaper model with better accuracy. So it's still the same process. Essentially what has happened is training time and cost is essentially driving the AI innovation. If I can train faster, if I can validate hypotheses faster, then I will go to better accuracy than my competitor. And we are all aware that 2021 ACM Turing Award winner was given to Professor Dongra for developing linear algebra libraries. And what has happened in the past 2 decades in machine learning, what people have realized is, well, machine learning started working, and what was the only hurdle was being able to train it on large data sets. And at some point of time, they had this realization that you could write essentially most of the computations of deep learning into a sequence of matrix multiplications or tensor operations. And at that point of time, all the libraries that were built by fundamental folks in high performance computing, that just came handy. And in fact, that is one of the very major anchor on which the whole deep learning revolution is built. And obviously, the award says is all that contribution was recognized as the best in the community. What is happening right now? So we were talking about, well, data started growing bigger and bigger. People realized linear algebra libraries are the rescue, but data continued to grow bigger. It's an exponential growth. Now we are at a matrix size that is kind of not sustainable, even with the current libraries or with the current ideas, right? So, by the way, there are a lot of algorithms for matrix multiplication. The one that is used in deep learning is still the dumb n cubed because it can be parallelized really fast. We still have not seen a regime where a faster matrix multiplication algorithm can be implemented and beat the parallelism that you can get from specialized hardwares or what we are seeing right now. But what is happening now is if we just extrapolate this, that you need larger models, okay, then you need to go to twice the size of the model to maybe half the accuracy or half the error rate. And people have done some analysis and it seems like you have to expect something about 500 times more computational resources that you are already burning right now. And it has a very bad implications also in terms of the carbon footprint. And essentially, companies are now thinking about, to get my accuracy better, I'll probably make $1 billion. But to get to the accuracy better, I have to probably spend $2 billion to train such models. And that has become a critical point, not just from the energy and the competition perspective, but also from a business perspective. So there was this article in New York Times in 2016. And obviously this is very relevant to the folks in the computer science theory community because they always think about going around the wall, right? I mean, there is one way of doing things, and that is hitting a wall, right? And this was written on Moore's law. And the statement was, the lesson is that as the engineering progress slows, I mean, in fact, this article talks about the death of Moore's law. The Moore's law means that we can double the power of our silicon every year or so, and that has stopped happening. And that means we cannot drive this AI revolution and a lot of other revolution. But then advances will come from human creativity. So after Moore's law, it became Hume's law, in which people are saying, okay, you know what, hardware and algorithms, both are equally important. They call it software and hardware, but it's the human creativity. All right, so with that motivation, here is what I want to talk about. So I'm going to talk about a fundamental sampling problem that occurs a lot in, especially in the machine learning literature, in many forms. It's an adaptive sampling problem. Then I'll show you if we can maybe make a dent in that sampling, which is some of my work since 2016. Then we'll be able to do faster gradient descent, is like the backbone of all the deep learning or machine learning algorithms. I'll show you how we can also do faster training and inference with especially large neural networks. I'll show you some results. And again, like, I come from machine learning world. We also build some systems and we'll show some results there. And in the end, again, if the time permits, I will talk about a cache efficient variant of, let's say, universal hashing, which has some very good implications in the recommendation system. So let's see how far we go. And again, I always want this to be as informal. If you have any questions, clarification questions in between, feel free to interrupt. How many of you are aware of the gradient descent algorithm? Okay, everybody, right? So in a gradient descent algorithm, you are doing an optimization problem. So you are trying to minimize a loss function over the data set. And it's an average loss, right? And the gradient descent algorithm says, okay, you know what? You start with and you want to find this argument. So you start with some theta t and update theta 0. And in every state, take a small step in the direction of the gradient. The gradient, the loss function is the summation over n. So the gradient is also the summation over the n, right? It's the linearity of the gradient. So what happens now here is, imagine now this n becomes a billion. So I'm trying to train it over a very large data set. Now just computing this step, which is, there is a direction. Remember, this average is a vector, it's a summation of a vector, it's a direction. And I'm taking a small step, generally very small step in that direction. Now to get the direction itself, I'm doing a billion computations. That's not quite good. So what works, and in fact, this is deep, like, almost nobody uses the full gradient. Everybody now do what is known as a stochastic gradient descent. In fact, they pick, instead of, and I'm just going to an extreme that you pick a random, you pick a small amount of sample and compute the gradient randomly and compute the gradient only on that sample and take a descent in that direction. Now, SGD is preferred over gradient descent in large scale optimization. It's known since like the 2010 or 20 long back, and it's basically nobody almost uses gradient descent. Every algorithm that you use in practice uses this. Now, it turns out that this is, like we can talk about the faster convergence, epoch times and all, but I mean, let's not go into all that because that's not what the point is. All right, now this algorithm kind of works because instead of doing a billion computation, I'm doing a constant amount of computation and still making a descent, and the direction is reasonable. Now, why does it work? If you go into the theory, it primarily works because a randomly sampled gradient is an unbiased estimate of the average. Or if you average it over a small sample, again, like it's very simple, right? I mean, it's a summation, and it's an average, and I'm replacing the average with an estimator. And if the estimator is unbiased, you can show convergence, a lot of nice problems. Now, if you look at the literature, you can always like, well, random sampling, can we do better? Of course we can do better. There is plenty of papers, and if you are like following some works on randomized linear algebra, leverage scores, if you have heard all these stuff, people are saying, okay, why don't you pick a sample? And again, like I think the notation is, this is basically you pick a weight, which is weight for xi. So now instead of doing randomly sampling an element xi and computing a gradient, remember I have n data samples, x1 to xn. Instead of randomly picking a sample I will pick a sample based on a weight. And it is shown that if weight is some sort of the norm of the vector, then this is kind of an optimal and it will give you better variance. So what it means is that your estimator for this average is going to be sharper. And it's also, it's a sum of a vector. There's a lot of terms in the summation. If I'm sampling the heavier elements more often, I'm probably likely getting better estimate. And the heaviness in a vector can be quantified by some sort of a norm. Okay, great. In fact, there are, If not, I'm not wrong, there are about tens of papers in top tier conferences that say that let's use this into it.
This again requires you to know the gradient.
Yeah, exactly. So now let's just think about it. I mean, this is what I'm trying to call a chicken and an egg loop. Right? So you are at a parameter theta t. Now to compute a sample, to sample xi in proportion to wi, you need to compute wi. There are n such wi's. So you are computing n such norms and then sampling from that. Now this may be okay if the norms are fixed, but the moment you sample and make a gradient descent update, your parameter has changed. Theta t minus 1 has become theta t. And so in the next iteration, you again have to recompute all this weights. So you are essentially doing an estimation of a quantity where the estimation cost is more than computing the exact cost. So that is little trouble. Okay. And again, like we'll go into later, but you can sometimes, or at least for the least square problem, you can look at the norm and decompose into an inner product in which one term depends on the parameter, one terms only depend on the data and the other term only depend on the parameter. And this will be used later, right? But this is the motivating problem of the sampling problem, right? So,
variance reduction in other ways.
but so this is again, this is the variance reduction is fine. So this will lead to variance reduction. So this will lead to faster convergence. But it won't be faster convergence than the exact because you're still doing an estimation. An exact will be better than an estimate. But if your estimator is more expensive than computing the exact, it just doesn't make sense, right? So if you look at all these papers, they will say this is a great idea. They will show some theoretical bounds and then say, well, in implementation, what we'll do is we'll assume these are kind of static and just use that as a sample. That is how maybe we can show something fast. But that actually doesn't work because the parameter moves very fast. All right, so this is the problem that we are going to solve. Before we go there, this is a disconnect between statistics and computer science, right? So statisticians, if you give me an estimator with 2 samples versus if you give me the same quality of estimate with 5 samples, 2 samples is always better. A computer scientist is this like, wait a second, what is the cost of getting those 2 samples? And the cost of getting those 2 samples is inferior than cost of probably getting 10 samples here. And maybe this is superior. In fact, we are talking about in practice we are trying to beat random sampling, which is a coin flick and pick an element, compared to computing a billions of weights and then picking certain elements. But nevertheless, the idea is interesting that you could do something better. But how do I go and do this sampling efficiently? Okay, so now we are going to take a little detour and talk about some fundamental data structures. Okay, and when I come to data structures, again, this is the whole idea of pointers, right? Data structures 101. Somehow fetching a memory location is a constant time operation. Okay. Now, based on this phenomena that if you tell me what is at a memory location, we call it as a constant time operation. We can create a whole theory of a hash functions, and I'm assuming everybody knows what a hash function here is. In a perfect hash function scenario, you want if x and y are equal, they should collide in the hash value. If they are not equal, they should not collide in the hash value. And this is 101, let's say, Google Microsoft interview question. If you're given n elements, remove duplicates from the element. If you do a naive Bayes n square, if you sort it, it's n log n. And if somehow the elements in the arrays are somehow that you can hash, right? It's actually order n. You can do duplicate detection in a constant time, standard insertion and search kind of a problem. Now, so duplicate detection is fine, but there is a whole family of a hash function. They're called locality sensitive hash functions. And these are stochastic hash functions, and I'll try to give you an example of what is the stochastic nature in it. But the idea here is these were designed for, it's kind of an extension of this. So this is great for duplicate detection. What about near duplicates? Now you will quickly realize that if I perturb something by epsilon, and if I want the hash functions to agree on it, then the whole hash function will degenerate, right? If h of x should be h of x plus epsilon, then h of x should be h of x of y for anything. So you cannot do it in a deterministic world, but in probabilistic world, you can do it. So there is a classical work in 97 and 98 by a bunch of folks who came up with a hash function, which is kind of a relaxation of that classical hash function. Again, I'm not going to the formal definition. This is an informal definition. And an informal definition goes like this, is that I will have a stochastic hash function, in fact, whose outcome are discrete integers. It's a distribution over those discrete integers. And the probability of agreement of the hash value will be high if x and y are similar. And the probability will be low if x and y are dissimilar. In fact, if you look at all the construction of those hash function, most of them looks like the collision probability can be written down as a monotonic function of the similarity between x and y. So the similarity is high, the probability is high. If the similarity is low, the probability is low. There has been many known families of hash function. In fact, we can even compute hash functions for inner products or some sort of a non-kernel, similarity that does not satisfy triangle inequality. That was one of the things that we showed in NIPS 2014. And if you are thinking about what these hash functions are, here is a classical example, and it came from a work of Jomans Williamson in 1990, the classical MaxCut paper. So the way it works is, let's say you have 2 points in the space, and you want to know their hash function, and the similarity that we are looking is an angle similarity. It's called the cosine similarity, if you're aware of that. Then what you do is you randomly spin or randomly sample a hyperplane passing through an origin. And if you are in this state, this is the positive part of the hyperplane and this is the negative part of the hyperplane. So the point lies in the negative part of the hyperplane, so its hash value will be -1. If it lies in the positive part of the hyperplane, its hash value will be +1. So in this case, there is a disagreement of the hash value. In this case, there is an agreement of the hash value. And it is, at least in two-dimensional, it is a one-line exercise to show that the probability that there will be an agreement is directly proportional to the angle. Right? There are 360, there are pi angle, theta over pi and 1 minus theta over pi. The nice thing that Jomans and Williamson showed was that this result also applies in high dimensions. All right, so this is one example of such hash function. A lot is known about these. But what is interesting is, so let's say now I want to do some sort of a near duplicate detections, right? So I have a data set of lot of elements and I'm trying to search for, I have a query and I'm trying to search for an element that is similar to the query. If it is duplicate, the problem is solved, right? We can do it with hash functions. But if it's not duplicate, but near duplicate, I can still solve it with LSH. And the idea is pretty much, so in this case, let's take, because these hash functions are stochastic, you can sample as many as you need. So let's say I have two independent instantiation of these hash functions, where collision implies high similarity, no collision implies low similarity. Now let's say these are my points in the database. So what I will do is I'll take this orange point, compute H1, and let's say for the time for illustration, my hash function only takes 4 values, 0, 1, 2, 3, and I'll encode them into bits. So what I'll do is let's say the hash H1 hash value of this orange point is 0, and H2 of this orange point is 1. And I'm going to index this orange guy at the bucket 0, 0, 0, 1. And similarly, I'm going to do the same thing for all the data set. 2 is just an illustration. Now let's say you give me a query. Now what I will do is I'll compute H1 of query, let's say it turns out to be 0, 1, and H2 of query, let's say it turns out to be 1, 1. Now the argument is that instead of looking at all the elements, which is an order n computation, I'm only going to probe this bucket. And this is a very interesting bucket because all the element residing in this bucket has collided in the hash value of the query twice in this case. That means, now this is an important point here, is just by doing some hash computation and the memory lookup, which is a constant time operation, I am likely selecting elements that are very similar to me, to the query. So you have beaten random sampling in some way, right? So for example, think of one world in which you randomly sample an element from the database. It is unlikely to be any similar to the query. But in this world, in a constant time operation, you're beating randomness. Right? Once you beat randomness, you are done. And in fact, this idea, if you look at the 98 paper, the essentially 98 paper is just replicating this number of many hash tables, creating more parameters and using union bound and all those tools that you all know to create like a high probability event for certain nice property that you want to test. And that became the popular LSH algorithm test. So H1 and H2 are these. So let's say my similarity measure is a cosine similarity. Then this is my hash function. If my similarity measure is Jaccard similarity, then there are other hash functions min hash. So I'm not going into the literature of what these hash functions are. It's a 25-year-old, let's say, literature now. A lot is known about these hash functions. So you're right. So this hash function is dependent on the similarity. So in this case, let's say if my similarity is cosine similarity, so I know what similarity I'm going to look for, and I will choose an LSH where the collision probability is some sort of a monotonic function of the similarity according to that. So H1 and H2 is the independent initial sampling from that family, right? So the family is the family of signed random projections, and I'm independently sampling two random hash functions from that family. No, I sampled twice in this case. You can sample independently. So once you sample independently, what this guarantees is that collision probability is cosine similarity, whatever, a monotonic function of a cosine similarity. This one also has an independent cosine similarity. So the probability that an element will collide with the query is this expression square in a bucket. Right? Now, to me, when I read this LSH paper, this was the key gadget. And everything else was basically getting around defining the problem and proving that we solved that problem. But for me, this was way more fundamental than what the problem was actually solved. This is actually doing adaptive sampling. So if you think about it, given a query and any X in the data set, I am sampling an element. If I just go to a bucket and randomly sample from that bucket, I will get the sampling probability to be this divided by the number of elements in that bucket. Thing to note here is the sampling probability changes with the query, but I don't have to compute it. You see what I'm saying? I don't care what the sampling probability is. It's some sort of a similarity. In a world of sampling, if I pose this problem to you as given xi, sample something to me in proportion to this, given a query and a database of lot of x, sample an element from a database in this proportion to this in the query. You will require order n work to sample because you first have to even compute the sample. But here I'm giving you a randomized process where you pay one-time cost of pre-processing, but every sampling is with this probability, and the query can be anything. The query is something that you choose. In fact, you can go slightly more. So instead of having one hash table and 2 being just an example, you can use k, some parameter k number of hashes here and L number of hash tables, and actually you get this sampling probability. The interesting thing to note here is that this is also monotonic in the collision probability. So P is the probability of collision. And you can actually sample X in this any K, and for any K and L, this is a family of distribution that you can sample. It's not a distribution. I mean, you can think of a distribution, but it's a family of distribution that you can sample from in roughly constant time. So the cost to sample is K and L hash tables and K, so K cross L hash computation, and that many L memory lookups. That is the cost of sampling with this probability. Now, why this is interesting?
This is not adaptive in the following sense that, fine, like you can do this once, and then pick a query, but if I sort of design an algorithm that sort of picks the next query that is based on what you have.
Yeah, it's not independent, right? It's not independent because there are ways to make it this independent in the sense that, let's say my K and L is small. Okay, so L is the number of hash tables. So I can pick like 1,000 hash tables and only use randomly sample 20 of them to pick this sample. So there are something that I can play that trick, right? So you're right. I mean, if I pick the query Q1 and Q2 is correlated with Q1, then the whole process is not independent sampling. Yes, it is not. Yeah, but this can solve a lot of estimation problem if there is a, because in estimation, sampling is fine. If you want an unbiased estimator, the variance is there, but sampling is still there. So let's look at come back to the problem of an SGD, right? And remember, we want to sample in which, so look at this expression here. This is theta t, so you can actually decompose, take out this norm, you can decompose it at theta t times 1 and inner product with xi and yi. Now what you can do is you can pre-process xi, y in a hash table, and theta t becomes your query. And theta t is allowed to change. So let theta t change, but you can sample in a monotonic function of this expression here. So essentially, still you are sampling heavier elements with more probability than the non-heavier elements in roughly constant time. So that's what we are going to do. That's what primarily what the algorithm and what the finding is. What you do is you pre-process it to some sort of an inner product hash table. Now, given the query, you query the hash table with this. Now you compute the gradient and you exactly know the sampling probability. So you compute the gradient and divide by the sampling probability, some sort of an importance score, and you get an unbiased estimator of a gradient. Now you can even show that this is not just unbiased, but it has better variance than SGD in a data dependent case. In fact, the variance is a data dependent variance in which if the data is very clustered, you get a better variance. But what is nice is that the cost of this is roughly like 1.5 times the cost of SGD. Compute a hash, throw a few buckets, sample. SGD, sample. So if this is really going to give you a better convergence, now you are in a position to see a difference. And actually that's what we see. So these are two different gradient descent algorithms. One is a linear gradient descent algorithm, standard gradient descent. The other one is an adaptive gradient descent, which is based on an accelerated gradient descent. All you are doing is in these two algorithms, the red curve and the blue curve, the only difference is your gradient estimator is coming from random sampling versus your gradient estimator is coming from an LSH sample. And you just run the algorithm and you will see that you get faster convergence. And this is not just in epoch. You will always get epoch-wise faster convergence, by the way. If you follow this algorithm, you will get faster epoch-wise convergence. But if every epoch is 100 times slower than every other epoch, so that doesn't work. This you can show running time fast convergence. So, going more towards like, okay, what have we done and what are the consequences? In fact, I have written several papers after this. What is nice about, if you look at this static sampling world, so there are n fixed sampling weights. So let's say the sampling weights are fixed and you are trying to sample xi with probability wi. If you want to take one sample, it's order n because you still have to create some intervals. If you want to do k sample, it's still order n because order 1 amortized for every subsequent sample. Once you create an interval, you generate a random number, which interval it falls, you sample at xk. Now you can actually get an analog of this even in a time varying situation. So now let's say you are in a situation where you have w1 to wn, but they vary with time t. And every time t, you have to sample xi with probability wi to the power t. Now, if you don't know anything about wi to t, it's already order n every time. But for a lot of family where wi to the t varies in some particular form, yes, it's subsequently correlated. That is right, because we are using the same data structures. But still, we could create a giant data structures and randomly sample to break the independent, like to break the dependency. We can still get a order 1 amortized kind of an analog. Now, what are the consequences of this? I mean, I think there are n number of consequences, especially in the machine learning world. There's one thing that a lot of people care about is the kernel density estimation, right? So for example, if you now just go into this area, if you just look at how many elements would land here, just ask that question, that's actually a kernel density. So now instead of having this LSH hash table where you have a list, you just have counters. And that count is an unbiased estimator of a kernel density. In fact, there are a whole family of kernel density that you can actually, we can do efficient kernel density estimator. There are several papers that I have written. You can even do compressed search. You can also do near neighbor search data structure, which is compressed. You can show that these kind of hash tables, if you use the counts, you can do differential privacy in them. And again, like I'm going to show you how to do adaptive dropouts for neural network training. But also like, sample an element with probability some kernel of the data and the query. You can actually get something very monotonic to this, and that can help you solve many estimation. So that's what, that's, I think also to me, what is exciting is this is a bridge between a randomized data structure, statistical estimations.
So, and some correctly that you are shifting from the compute to the memory. Now, I think from hardware perspective, you're reducing some computation, but you are using more memory.
That is true. So that's always the case. See, data structures means you're using memory.
So do you have any idea, like let's say you reduce 2x and you use the
So the memory depends on KNL, right? How many hash tables you create. And again, remember, these are not the actual data set. These are just the pointers. So let's say order n for each hash tables, order n into L. That's the memory. But the compute cost is order 1 instead of order L, right? Or order L or order K into L, if you may, instead of order N.
Sketching or other techniques are they useful in this kind of problem?
Yes, yes. I mean, so essentially what I just showed you, once you go into the counters, you are essentially having count sketches where the hash functions are LSH. So there was a paper like distance sensitive Bloom filter by Mitchenmacher, and that was done for some like near duplicate Bloom filters, right? So Bloom filters just do exact matching. You can do near duplicate matching, but they were all talking from a perspective of search and near duplicate matching. Here we are doing statistical sampling, and I think that was the fundamental. I think the fundamental tool is actually doing statistical sampling, adaptive sampling efficiently, and you can convert that into that sketching searching problem. But this tool by itself can solve a lot of statistical problems. So now you're getting unbiased estimators of kernel density estimator with better variance and compressed memory. And that is actually pretty useful for a machine learning community. Yes.
Sorry,
Of course.
stuck at the memory. So now, does it also depend on system configuration? Let's say we have 3 levels of memory.
Yes, I mean, so you're talking about the memory hierarchy perspective, right? I mean, yes, it depends. So it depends on what system you're executing this. Plus the access are randomized. So if you're relying on something like GPUs, that will not work really well, right? Because it's not a coalesced access. I'll talk about a few of those things. Okay, so now let's go into the deep learning world. So how many of you are aware of the backpropagation algorithm, right? So again, like in deep learning world, what happens is there is a neural network. The inputs are just the vector. So you just treat image or whatever object is in terms of vector. Then these neuron activation is some sort of an inner product followed by some thresholding. Then you get another vector and then you process it in another vector, so on and so forth, unless you get to a prediction, and then you backpropagate the error, which is again a gradient descent to correct. And as I mentioned, a lot of these algorithms, they use matrix multiplication to do it because they assume dense computations, like you have to do all the computation. But it is known to the community that backpropagation, the algorithm that is still currently being used, is very wasteful. And why is it wasteful is because, I mean, there are various reasons, like the way people do thresholding, they actually ignore 50% of the compute. In fact, there was a paper in NIPS around 2013 where they say that, well, you can actually throw 90% of the neurons. If you compute all the activations of the neuron and only pick, let's say, top 10%, you'll be fine. In fact, what they call it as an adaptive dropout, why don't you do a Bernoulli coin on every neuron, which is in proportion to their activation, and sample, let's say, 1%, you will still get the same accuracy as the original network. There were papers like this in 13, 15, so on and so forth. But from an algorithm, from a statistical perspective, great, right? There is some sort of a notion of efficiency. From an algorithmic perspective, wait a second. You still have to go and compute all the activations of the neurons and then sample from those activations in proportion to their activation. In fact, this paper adaptive dropout says compute all the activation, then put a Bernoulli coin on PI, P1, P2 on all of them, and sample 1% with that proportion to that probability. Now, if you have seen what we just talked about, well, maybe I will not use a Bernoulli coin. Maybe I will use some sort of 1 minus a monotonic function of that activation and still sample in that proportion, but I can do that efficiently without actually computing all the activation. Because again, computing all the activation, that's order n work. I've already done it. So why should we care about that, right? So in fact, this is what, like a lot of people is talking about sparsity as a way to go forward in neural networks. And again, I want to make a distinction here. It's not a static sparsity. Static sparsity generally means you throw away parameters. You say certain parameters are not useful. But we are doing what is dynamic sparsity. So we are going to pick for every input the right set of neurons, which has larger activation. In fact, we'll mimic the adaptive dropout process in which I will sample in proportion to the activation in sublinear time and propagate the neural and sparsify the neural network. So my computations in the neural network, so imagine this is a billion parameter neural network. So when you take the input process, that's a billion computations, you look at the input error, you backpropagate 2 billion computations. What we are going to do is we are going to take something, pick 1,000 parameters, do 1,000 operations, compute the error, backpropagate only on 1,000 parameters, update some hash tables only on 1,000 parameters. So still few thousand operations. Yes.
But then you are training multiple times. constant you are telling this?
Actually, that is we are going now into the what is the convergence of this procedure, right? The issue here is that if you even look at the actual literature of let's go with the usual deep learning process. Here is what will happen. If you have a billion parameter network, you will compute the gradient. 99% of the gradient will be like 0.0001. Okay. And then you will you will still update all of that. And then to these days, NVIDIA will tell you only do 16-bit or 8-bit arithmetic. That means you will anyway wash away those. So you're still going to do this, except in a dense way, more or less. So essentially, it doesn't hurt. I mean, what we have seen is the convergence rate remains the same. Okay, so I'm going to show you so before we go, the thing to note here is that the activation of a neuron is also just an inner product. So we are still going to use that inner product search. Again, I'm not going to, so I've written several systemish kind of papers too, as then can we make this hash table process very efficient and do it in constant time in practice? The answer is kind of yes, but here is how the algorithm will look like. So what we'll do is we'll initialize the neural network. We'll pay one-time costly cost of processing all the neurons. Neurons are just weight vectors. We are going to process them in some sort of an LSH inner product hash tables. Now you show me an input. I'm going to hash the input, go to a bucket. Let's say bucket tells me 1, 2, and 5. I will only pick neurons 1, 2, and 5. And I will compute the full activation of neuron 1, 2, and 5. I won't touch 3 and 4. I will assume their activation is 0. Now I have a sparse vector where this is 0 and this is what I computed. I will again go to the next hash table, get this, and proceed. Now things to note here is that just by hash computation and few lookup, I get a sparsity of the pattern of the neural network. Now, if the number of parameters that I touched is, let's say, few thousand instead of billions, this is a huge savings. Okay. What I will do is then I will feed forward on this sparse network, compute the error. Parameters that don't participate will have gradient 0. So I don't have to worry about that. I will only backpropagate and do the gradient descent only on these weights. And once I've done updating the weights, I will go and update the hash tables. So if I am touching 1000 parameters, then all my operation forward, backpropagate, update the weights, update the hash table is only of the order of 1000, not millions or billions. Okay. And there is one bonus here is that you could do data parallel gradient descent. So generally gradient descent is a sequential operation. When you compute the errors for a cat and update the cat, you are likely updating all the parameters, assuming dense operation. And so if there is another image that you even have to compute what is the error, you need to first make these updates into the system before even you can go and compute the error. But if it so happens that this network is very sparse, the way we are doing it's very sparse, then it's likely that these two images will pick more or less disjoint set of parameters, and so I can update them in parallel. In fact, there is a paper called Hog Wild written by Michael Jordan and folks where they showed that so long as the norm overlap between these parameters is small, this process will still probably converge to the right solution in terms of like obviously in gradient descent mode. So this is the algorithm that I've been focusing on for the past 4 or 5 years. In fact, with Third AI, we actually are doing a commercialization. So I'm working with a lot of undergraduates building a C++ system for this algorithm and exposing them in Python so that people can use it. And we have optimized library that works on laptops, ARM, x86, and this is the algorithm. I'm going to show you some numbers. Here are first set of few numbers. So I'm training some Kaggle recommendation model. So this is Amazon product search with 670,000 products, sorry. And it's a giant neural network that you need. So there are two cases. We train, let's say, a relatively smaller, which is 200 billion parameter network, and then we'll go to a bigger, which is 1.6 billion parameter model. Remember, when the model size is 1.6 billion parameter, that's already even 10 gigs just to store the parameters, right? And the data is also big. Now I'm comparing, these gray lines are actually Google's TensorFlow implementation. So it's an optimized package for that hardware. We have also put NVIDIA A100, like a GPU that costs you about $10,000 per GPU, 10,000 US dollars. And this blue line is the system that we developed based on this algorithm. And you can see that you get the accuracy climb over time. The whole spectrum is higher, even if when you compare it on GPU versus CPU. Now, what becomes more interesting is when you go on 1.6 billion parameter model. Now, GPUs don't have a lot of memory. So the reason why they can do thousands, tens of thousands of cores on a small set of memories because their architecture does not allow their memory to grow. In CPUs, you can have a lot of memory because there's memory hierarchy. GPUs works in a different way. So on CPUs, it's not difficult to still fit this model on a CPU and you can train it. Obviously, it will be very, very, very slow if you train it in a traditional way. With this algorithm, you can train it even faster than 4 A100. That's like $50,000 versus a $1,000 CPU.
Training, not about inference.
Here only the training cost, but there are actually tricks. We actually wrote a paper in MLSys, but you can see, remember, even the forward pass was sparse. The problem with inference is if you go wrong, you make a wrong prediction. So sampling is fine, but you have to be really good on predicting the label. So if you fix for that, you can actually even get faster inference. Yeah, so this is Xeon Platinum. Which one? Yeah, I mean, this is, this is, it depends. Again, like these are not comparable processors.
Yeah.
And I think once we bring the computations down, I think memory latency becomes the issue. So the processors that have better memory latency, this gets better. So I think this has better memory latency. This process. Yeah, we don't know. I think this was AMD Epic and it has 4 pods. And we were training one model, so it is quite possible that it was replicating the pods and communication was. Yeah, we are using all the threads, yes. So what we do is we do data parallel gradient descent, and when we do data parallel, it's over all the threads. No, not really. I mean, we just put our hands on whatever reasonable ones we can get. But yeah, you're right. I mean, this architecture had some memory latency issues. But this is a laptop. This is an Apple M1 laptop. I can train something faster on a laptop than A100 GPUs. This is a 200 million parameter model.
Because in laptop you don't get really very high compute.
Yeah, that's true. But then we don't need a lot of compute for our algorithm.
And then those are servers.
These are not. I mean, you can call it server scale. I think this is probably 20. This is probably 28 cores, and this I think is maybe around 30, 35. I don't know, something around that. Depends, or maybe less, 14 or 16 cores. I don't know. And this one is the new Apple M1. So if you train it with your TensorFlow optimized TensorFlow package for that Google recommends or whatever Apple recommends, you'll be terribly slow. No wonder if you were to see this, you will say this versus this. Let's use this, but this is very expensive. All right. Now the good thing about it is we recently also deployed this in production. So I think this was a blog that just came out of Wayfair, where they say that they are actually getting a lot of benefit in inference time and more relevant and faster browsing experience for their customer. So this system is actually even deployed. Again, like this has more, like a consequence in the machine learning world. I think there are a lot of packages out there which helps for prototyping, but there are not a lot of packages which actually let you explore the compute accuracy trade-off. So that's the thing. We can also show some nice experiment with the carbon footprint. Like we can train Roberta, which is the state-of-the-art NLP model, which roughly takes hundreds of light bulbs energy. We can train it in an energy of LED to the same accuracy with this kind of approach. Anyway, I think maybe I do not have much time to go into this thing. I'll stop here for questions. This is another work that that we presented in MLSys. The moral of the story here is if you're aware of universal hashing, then you can make universal hashing cache efficient by hashing in blocks. And the nice thing about that in machine learning is it's not just better in terms of cache efficiency, but it also is better in terms of variance. We were actually surprised. We were not expecting, because once you do blockwise, there is a correlation, but it turns out that the correlations are actually, helping the variance, especially when it comes to dimensionality reduction in machine learning. But having said that, I mean, I will like to stop here and say that this is the most exciting time to be an algorithmist in the machine learning world, because it seems there is no other route, right? Hardwares are what they are. The Moore's law has ended. We are not going to get more from parallelism. The models are growing, the data size is growing, and where will the good ideas come from? And it's actually, this is what I keep telling my student, that if somebody comes to you and say, hey, you know what, we need to get 1.5 or 2x, then you can stay on the same idea, roll up your sleeves, use all the tricks in the textbook, you'll get 1.5 to 2x. But if you're living in the world where someone comes and say, well, we need 100x, 1000x, you have to go to the drawing board. You cannot stay with the current system because it's not going to give you 1000x. So if you want to see 1000x or 100x improvement on the backpropagation algorithm, you have to modify the whole algorithm itself. And I think this is the right time to go to the drawing board and look at what options are available. And hopefully I have demonstrated to you that the intersection of data structures and statistics, there are some very interesting ideas that can help the machine learning literature. And with that, I'd like to stop. Thank you very much. Yes.
So, we also tried your algorithm with networks where there are like long tracks.
No, we tried mostly with the recommendation models because some of the biggest models are recommendation models, right? So no, what do they call DLRM, fully connected networks, DLRM, and we do have some attention models too for NLP.
So no,
No CNNs yet. In fact, I mean, we were even thinking doing CNNs until the world has started to show that they are anyway diverting away from CNNs to language transformers, so vision transformers. So we might just do it on vision transformers then. Actually, it's just implementation. When again, like idea-wise, CNNs can always be written as a fully connected network with a structure, right? But to be able to beat GPUs, you might need like a very specific kind of an implementation for convolutions and hash tables. We had some ideas. We thought that we'll implement it, but then we realized that we are already in the transformer world, and the world is moving towards vision transformers.
one thing is in vision transformer, this part, or I would say most of the part is not training those weights. Like you have an encoder, you have a decoder, most of the part of the vision transformer is just matrix.
Yeah.
It has less part which consists of the training. If you see for the whole spectrum of the whole transformer model, do you know how much speed up you are getting for the whole transformer?
No, this is end to end. So whatever I'm showing is end to end.
Okay, okay.
Yeah, there's no, I mean, we are not breaking down anything and saying that I'm only looking at this network. This is end to end training time. Whatever I showed is end to end. But again, like these are large networks, so they will stall anyway. So it's
So you are showing that you can also products. So
I mean, we are not approximating. Right now we are selecting, but that's a good point. We can still approximate because you can invert the similarity from the collision probability. So you can also estimate, but we haven't tried that yet.
so then if you do that, you can also accelerate the inference.
I believe so. Yeah. I mean, again, right now we are just using sparse way to accelerate the inference.
This point about sparsity, you say discourage, so not the hardware, like you have to discourage this kind of unstructured sparsity.
Because they are not good at it. If you compare head to head, that I'm doing 1000 operations on CPU and 1000 on GPU, the 1000 operations, if they're of a particular kind, only then they will be fast on GPU. Otherwise, CPUs are faster. So random access is better on CPUs. And this is one of the shortcomings of this algorithm, that it has to be random access. And there we have still like we wrote few papers with Intel where we still were able to do some sort of a prefetching or something to get it faster. But yeah, I mean, getting it done on GPU will be another work. That's a good point.
Other hardware things for accelerating smaller, especially hardware accelerating that will also be.
That will also, so most hardware accelerator rely on memory coalescing a lot. Yeah, that's true. I am not doing, so we are not doing matrix multiplication. I mean, you can think of it as a smaller matrix multiplication if you want to, but it's a selection. First, the first part is selection, and then we compute, let's say, 3 multiplications in this case. We are not computing these, we are not computing any activation for these guys. But then note, there is no matrix multiplication because if you take another vector, maybe it will go to 2, 3, and 5. And you don't want to compute 3 for the first guy, you want to compute 3 for the second guy. Yes, you can break it into smaller matrices and still do matrix multiplication, which will make it faster. But you still have to do the gather and like aggregate operation. Right now, the way we are implementing, because anyway everything is data parallel, we have separate threads for every element in the batch. Yeah, so we are, let's say if the batch size is 100, every element goes to a different thread and does the computation. So the thread is enough saturated and then we can still do it. Yeah. But yeah, that's a great point. If you want to still utilize some vectorization, we could do that. Yeah, yep.
Slightly more like adversarial view of this thing. So you have fixed the hash functions and you are running these. And so let me take this as a black box result that it will converge to, it's converging quickly, right? Like you are actually shown that. But this also tells me that, so there are these results that say that you can perturb images, so the cat becomes a panda with changes that are undiscernible to the eye. Are there, so those sorts of adversarial attacks, are they also revealed by such methods?
Actually, that's a great point. In fact, we are thinking the other way around. We think that these guys will be more robust to the adversarial attack. So what is happening in adversarial attack is now you think in a high dimensional boundary, right? So every class, let's say I have two classes A and B. In high dimension, everything is near the boundary, right? So the boundary between good and bad and all the data points are in the boundary. So all I have to do is to figure out a direction in which it will cross a boundary, and that's my adversarial attack. Now in this case, because it's a randomized system, it will have some, because of randomization, we believe, again, like we haven't seen that yet. It could still be true because at the end of the day, if you get a boundary, maybe our boundaries are a little more fuzzy because they allow for perturbation. So that's why, again, like, but since, see, I think adversarial is a little more fundamental to machine learning. If you're really accurate, that means in a high dimension, you have two data points, which one is cat and other is dog. You can show a cat that looks to humans like a dog anyway. So they are very close. And then there is a boundary somewhere striding. And if your classifier is accurate, it is respecting some boundary, right? And all you will have to figure out is that direction, and then you will just be able to cross it.
I guess like the way I was thinking was like there are like dissimilar points that will have, that's just a limit information theoretic limit. Hash functions will have to violate. So I look at, again, a very adversarial and a worst case, this is the theoretician speaking. So you have these hash functions, I can find very dissimilar points that will collide.
Yes.
So for them, at least, like, let's just look at the first layer, they will end up having the same activation. So
yes.
In that sense, I'm saying there are dissimilar images that you can.
Yeah. So that's actually a great point, and the reason why the adverse see, there is a lot of redundancy. The reason why machine learning work is because you will never see green and blue the other way around, right? You will never see the green on the top and blue. The sky is always on the top of the grass, right? So there is a lot of structure and a lot of redundancy in the world. Now, if I may, then let's imagine that there are thousands of concepts in the world, and I am sparse in those concepts. So the concepts could be nose, eyes, ears, wheels, antennas, and all we are doing is the feature detector, right? So if you want to predict a face, you get a nose right, you get eyes right, you maybe got ear wrong, you got the mouth right, you still is a face. There is not many things in the world that has nose, eyes, mouth, and no ears, and not a face. Right? What I'm saying, see, so even if you miss few, that's fine. Now, even if you get few wrong, like let's say you got an antenna, somehow antenna fired. Right? How many times an antenna, eyes, nose, and ears come, and it's still a face? Maybe it's a robot face, but it's still a face. Right? So, see, neural networks, you're absolutely right. If you think about what can go wrong, everything can go wrong. I'm doing a very crappy approximations to tame neural networks. But if you think about it, SGD is the crappiest approximation. I am replacing a billion sample average with a one sample average, and I'm still fine with it. Then NVIDIA comes and say you should just use 4 bits. Forget about your gradient. Just quantize it to 4 bits. That will still work. And the reason all these things are working is because of the redundancy. So the reason why we are saved, and you're right, what you're saying will happen and does happen. But people evaluate machine learning models on average accuracy, average error on a real data set. Right? If you take an adversarial data set, I think you can take this to, probably, yeah, I don't know what will happen.
Yeah, but
What?
There's another talk.
we need for
Hi.
Oh,
How are you there?
so the question was?
We have the hash functions.
Yeah.
They are not public. Is there a way to have them?
No, the hash functions are public. I mean, these are like cosine similarity hash function. Depends on what similarity you are using. But yeah, the random seeds are not public. It depends on your, the coins that you are using depends on your.
My question was, how do we guess those functions? And we can guess only then we can perform.
Yeah, exactly. So from a attack perspective, what you're saying, it might be harder. That's what my guess is. It might be harder.
Because,
Can we please take all the questions outside? There's another talk that's due here. Before we go, let's just give a big hand to
Thanks a lot.
Thank you.
Thank you.
You can have the rest of the questions outside of the house.